Okay, we're back for part two here, and uh, as you can see, I've done a little of the background work. That's so you don't have to watch me do some stuff, that takes a long time on this. I'm going to try and go fairly quickly through this, I hope. Remember that if I'm going too quick for you, there's a couple things you can do. First of all, you can ask to have it paused a little bit. Also, remember that the links for these videos are on the website and on YouTube. These videos are on YouTube, so you can rewatch them as many times as you like. And also, I will post my version of these notes on Facebook like I normally do, so that you, if you want to, you could just listen along and then print off the notes. But I'll leave that up to you. Um, so we just skipped that big long thing about the rigorous definition, and we're on to some examples. So we've got a function, and what's weird is we don't know what this function looks like. And we want to determine each limit by graphing whatever a limit means, and this example will help us define what a limit is. But first of all, we need a graph, and since we don't know that, what the graph looks like, we might look for some points. After a little while, you might try some points and get some nice values. So all these values are values that work out nice, and you end up like this, and say, oh, I recognize that. That's a half circle. Should have I recognized that this was a half circle? And maybe I'll show you why. Um, Remember, if this is f at x equals this, f is the same as the y value, and if I square both sides, then move the x squared to the other side, this is the equation of a circle like we saw in grade 10. In grade 10, we saw circles that look like that. And so this is the equation of a circle. This is the equation of a half circle. Now, I wouldn't have expected you to remember that. There's the table of values. There's the graph. So we're talking about a limit as x approaches 3. So what we're interested in here is when x gets close to this value right here is where do the output values go? Well, when I get close to 3 from the left, it's getting close to a value of 4. Right? Same thing if I think of values of x getting close to 3 from the right, this function I'm thinking about is getting close this way. So this is values of x are getting close to 3. The values of y are getting close to 4. And in fact, that's what this limit's equal to. Because the left limit and the right limit are both equal and equal to 4, then we say the limit exists, and it's the value, the output value, y equals 4. And so this is kind of like our L from before. As x approaches 5, and that little minus, remember, means from the left. X approaches 5 from the left. So this idea now, x is getting close to 5. Well, what's the function doing? And I kind of goofed up my graph there, but I'll fix it. What's the output doing? Well, when x gets close to 5, there's 5 from the left. X is getting close to 5 from the left. Then what's the output values doing? Well, they're getting close to 0, aren't they? Right? And in fact, if we tried values like x is 4.9 or 4.99, values that are getting close to 5 from the left, we'll see that this value would be getting closer and closer to 0. What's interesting about this one is what happens if we're on the right of 5. If we're on the right of 5, notice there's no graph out here. And in fact, if we're at the right of 5, things like 5.1 or 5.01, this ends up being too big, right? 25 subtract some value that's a little bit bigger than 25 is going to give you a negative underneath the root sign. It's not defined. So this limit, well, it does not exist because there's no function value. Where is this heading towards? Well, it's nowhere. It's like the function is undefined for that domain. So this does not exist. And so putting those together, notice that in our definition of a limit, we had that the left-hand side limit and the right-hand side limit had to be equal. So since we've got one value that's equal to 0 and one that does not exist, well, that means this limit, the overall limit as x approaches 5, does not exist. Notice in this statement is a stronger statement than the two little statements x approaches 3 from the left of f at x. We said that's this one, as x approaches 3 from the left, f at x approaches 4. And then this one, when we say this, we mean both of these. That's the definition of the limit of a function. Okay, next one, awful expression here. Awful expression. And we're interested in the limit as x approaches 2. Well, notice that, up here, we probably could have just, we did actually, when x was 3, we just substituted in and we got 4. Can we just substitute in when and get 4? Well, not really, because here, when x gets closest to 0, or sorry, to 2, the top gets close to 0, the bottom gets close to 0, I'll get 0 over 0, and something goofy happens, right? We can't just substitute. This is kind of like our instantaneous rate of change, our tangent limits from the last couple of days. So we have to, let's split this. We split it into the two limits. The limit from the left of this function, and this is a nasty function here, that's what I'm calling f at x. These values we think of numerically, x approaches 2 from the left, are things like a little bit less than 2, 1.9, 1.99, 1.9999, and then at 2, of course, it's undefined. And I just clunked those into my calculator. You can check my work if you want, but it looks like x approaches 0.25, or a quarter, from the left. Doesn't it? That's what it appears. It'd be nice to be able to show that algebraically, perhaps. And notice on the right, values, if 2's right here, values on the right of 2 are things like 2.1 might be back there, then 2.01, then 2.0, and we're sneaking up on 2 from the right, numbers that are bigger. And I'm kind of thinking of pinching in towards 2. If I read this part of the table backwards, 0.24, then 0.249, then 0.24999, it approaches 0.25, or a quarter, from the right. Now, when I think of these two things together, these are two limits, right? This is the limit as x approaches 2 from the left of f at x. That's equal to a quarter, we said. And this is equal to a quarter. It appears, anyway, that these two statements together means that we can say that the limit as x approaches 2 of this thing exists and is equal to a quarter. The left-hand limit is equal to the right-hand limit, and all is wonderful in the world. Next. Oh yeah, that was that thing about the circle. Okay, sketch the graph of a piecewise function, then determine this limit. Piecewise functions you took in advanced functions last semester or last year. And I've got 3 pieces, and I've sort of broken them up into pieces so we can think about how the heck we're going to graph them. The first piece is a parabola with the vertex at 4, 2. So vertex at 4, 2. And the stretch factor, there's no stretch factor, so it's a normal parabola. And you might want to wait a second to graph this, because this parabola there is only true for x is less than 4. So there's the cutoff at 4. Of course, I blew that. I'm going to have to move all my points one spot because I blew it, didn't I? Thanks for telling me. There's 4 right there now. There, that looks better. And so this function is only true, yeah, nice. This function is only true for values of x less than 4. So here's the values that work. And notice, less than 4 means that I should have not counted that point. It means anything that's on the left of there, but not including that one. That should be an open circle because I don't want to include 4 in this chunk of the graph. Notice for the second part, this part here, should I do it in blue? Yes, I should do it in blue. That part right there is, it would be a line, y equals -4, but it's only for one point. So for that single point, we're way down here. There's -4. For when x is equal to 4, the output is -4. And notice this is just a goofy made-up piecewise function. And then for the rest, it's a square root function. A square root function that's been moved right 4 and and up 2. Right 4 and up to, aha, it's going to start there. Would be colored in there, but again, greater than or equal to, not there. And then the parent unstretched root function looks something like this, right? There's y1, y2, and y3, okay? And so this limit, let's talk about this limit. Well, let's talk about the limit from the left. The limit as x approaches 4 of f at x means we're following this green line, right? They're following this green line. It's getting closer and closer and closer to an output of 2. The left-hand limit is equal to 2 because my graph is getting closer to 2. And that follows the parabola. But if I'm on the right of 4, then on the right of 4, I'm on the purple graph. And as x gets closer and closer to 4 from the right, I'm following the purple graph, and it's getting closer to 2. So what does this mean? The left-hand limit is equal to 2, and the right-hand limit is equal to 2. So that tells me this limit exists and is equal to 2. Which is weird, of course, because that function value is different. This is not equal to -4, which is the value of that function. Note, f at 4 is not equal to the limit value. Weird. Weird, weird, weird. Okay, and so based on this graph, we're going to answer some true and false questions, see if we can understand what's going on with these limits a little bit better. So we got the limit as x approaches a may exist even if f at a is not equal to the limit value there, and even if f at a does not exist. Well, that's exactly what this last case was, right? We had x approaching 4, a was 4, from the left and the right, both equal 2, but f at 4 was equal to -4. And even if f at a doesn't exist, even if we wipe that point off, that limit is still going to be equal to 2, even though the function might have been not defined there. Maybe that function's not even defined there. So this is 2. So if the left-hand limit is equal to L and the right-hand limit is equal to L, then the limit as x tends to a of f at x equals L. That is true. That's actually the definition of the limit, of course. That's the definition. What about this one? The limit as x approaches a of f at x equals L, then f at a equals L. So if the limit exists and equals to L, that means the function value there must be equal to L. No, because we saw that in this example, right? This example, the function value was equal to -4, but the limit was equal to 2. So this is a big F. F for false, F for fail. It doesn't work. All right, so let's see if another true false. Limit as x approaches a of f at x equals f at a. So that's the idea of, in this case, if it was filled in, the limit value is equal to the function value there, then the graph y equals f at x flows through the point. That's not a very mathematical term, but it flows through the point a at f at a. that would be the point A at f at A. And this idea of flowing through, that's true. So if the limit value is equal to the function value there, then it flows through. We can go right through that point nice and easy. Doesn't have to be, though, for the limit to exist. It could be L. But in this case, this is this extra idea of being able to flow. Example 5. Now, warning here, I got a lot of this work done already. You can sort of copy as much as you like or not. The answers are actually fairly quick, and I've written down more work than we would ever need. So here we go. Let me get the right color pen. So I have the limit as x approaches 2 from the right of x minus 3. Well, this is just a line, right? And if I wanted to do this numerically, from the right would be values that are a little bit greater than 2. So I think about a table like this, and it looks like it's getting close to -1. And in fact, on the graph, this is the line y equals x minus 3. And I think of the x values getting close to 2 from the right. Well, what's happening? The function value is getting close to -1. No problem. Say, well, Restall, why don't you just substitute 2 in there? There's no problems. There's no issues. Why don't you just sub? And in fact, if we can, we will. So this one is a crazy function. There's the graph. I'll remind you in a second about where that might come from. But if we want to evaluate a limit numerically is from the table like this. I'd pick values that are to the right of 1, 2, then 1.5, 1.1, getting closer to 1 from the right of this function value, and I work on my calculator, and it looks like it's a quarter. Looks like it's a quarter. So, well, if you just substitute in, did I do 1 or 2 there? 1, yeah, 1. Squared minus 8 is -2 over negative, well, that's a 9, sorry. That's some great handwriting there. Is a quarter. Can I just substitute it in? Yes, you can, but what happens if it was one of these nasty values, right? These nasty values where the graph is doing weird stuff. I can't substitute in. Does it mean the limit doesn't exist when there's nasty values? No, because we saw that earlier. There was one earlier in the lesson, this one here, where there was a nasty value at 2 and the limit still exists. It was equal to a quarter. So and I couldn't just substitute it in. So that's kind of weird. Now, as far as how would we ever graph this if I didn't have a graphing calculator, remember, you did all that rational function stuff. We know that there's going to be asymptotes at 3 and -3 because that'll make the bottom 0, and then there's some stretch factors, and you can get some points and all that business. That's lovely to get a graph. And again, we just need the graph for a sketch. Here we go. Here we go. This is a good one because I can't just substitute 5 in there, right? If I substitute in 5, I get 1 over 0, and we don't know what's going on then, right? So there's a couple things I could do. I could look at the graph, or I could look at the table. Think of the left-hand limit. So when x is a little bit lower, a little bit to the left of 5, things like 4.8, 4.9, 4.99, well, what's happening? And I just use my calculator, the value is getting bigger and bigger negative. And I can see that on the graph. As x gets closer to 5, the outputs are getting bigger and bigger negative. In fact, this value, the limit as x approaches 5 from the left, is -infinity. Similarly, from the right, it's equal to +infinity. So what can I say about this limit altogether? Well, is the left-hand limit equal to the right-hand limit? No. And in fact, then, the limit as x approaches 5 of f at x does not exist. Okay. Well, hopefully you followed that okay. And of course, you should have lots of time to discuss. The homework is on the page, and good luck with it. We'll chat more about limits of functions on Friday.